All right, let's talk a little more about how we might visualize constant speed and velocity. So to do that, we're going to go to an app. And in this app, we're going to set a few things. So we've got a red object and a blue object. And right now, I am going to make them both have, actually, zero acceleration. And I am going to make, I am just going to give the blue car some speed. Okay, so it's a speed of 7. So what that means is that every second it's going to increase its distance by 7 meters. So imagine that this car has an oil leak, and as it moves during the next 100 seconds, it's going to drop a drop of oil every second. So the red car is going to be at rest, and the blue car is going to be moving at 7 meters every second. Or actually, I'm sorry, the blue car is traveling at 5 meters every second. So every second, it increases its speed by a certain amount, right? So look at the blue car. The blue car is only traveling at 5 meters per second every second. And as it does that, it makes a drop. All right, so what we're going to do is we're going to compare the motion of two cars. And we're going to look at a car that's red, that's traveling at half the constant speed of a blue car. They're going to be tracking their motion with an oil drop. So imagine they both are leaking oil, and every second they drop. So if you're traveling at 5 meters per second, then every second you will drop a drop of oil, and you will have gone 5 meters. And if you're traveling at 10 meters per second, you will have gone 10 meters. So let's look at those diagrams to see what those look like. These are called dot diagrams. And they only show what the car is doing over time, right? The distance that they travel every second. So you can see that the car that is traveling slower drops every 5 meters, but the car that is traveling at 10 meters per second makes a drop every 10 meters, so that every 10 meters every second, so that it goes twice as far every second than the red car does. But notice too that each of these drops are equally spaced regardless, and that indicates that they're traveling at a constant speed. So these ticker tape diagrams show a great way to visualize something that's traveling at constant speed. If it's traveling fast, the dots are separated further apart than they would be if they're traveling slow. But they are traveling at a constant speed, and we know that because the dots are equally spaced. But what happens when we speed up? So when we speed up or slow down, in physics we call that acceleration. It is a change in velocity over time, so it itself is a vector, and the numbers that we put in for velocity are vectors. One way to denote that is to put a half arrow across the vector quantities. So let's just do an example. If you increased your speed from 2 meters per second east to 4 meters per second east in 2 seconds, then your acceleration would be your final, which is 4 meters per second minus 2 meters per second all over 2 seconds, which is 2 meters per second divided by 2 seconds, or 1 meter per second squared. But what if instead you were traveling 4 meters per second east, and you then, after 2 seconds, were traveling 2 meters per second east? Your acceleration would be 2 meters per second minus 4 meters per second all over 2 seconds, which is going to be negative 1 meter per second squared. Now, this negative does not mean that you're traveling west. What it means is that as you travel to the east, this was your velocity vector, you were slowing down. That's what it means. It means that if you were traveling to the left, to the west, that you would be speeding up. So this sign here means that you speed up to the west, which means that if you're traveling to the east and your acceleration is to the west, you're going to slow down. The only way for you to speed up is if you're traveling in the same direction as the acceleration vector. So think about it. As you get faster, the dots get further apart. So if you are, let's say that these are 4 ticker tapes, and we're going to pay attention to number 3 and number 1. In both of these situations, a car is moving to the right. So as the car moves to the right in number 1, the dots go from being very close to being further apart. So it is changing its speed. We know that it is accelerating. And in this case, because the dots are getting bigger to the right, the acceleration is to the right. So the car is speeding up. In number 3, though, as the car moves to the right, the acceleration is really getting bigger to the left. So we know that the car is losing speed, and the dots get closer to each other. So the rules of dot diagrams are, if the dots get further to the right, it gets faster to the right. If the dots get further to the left, it gets faster to the left. If the dots are the same distance apart, then it's a constant speed. The further apart the dots are, the faster, and the closer apart, the slower. Let's practice. So let's imagine that in all of these, the car is moving to the left. So what we're going to do is we're going to put the direction of acceleration for all 3 of them, and the type of motion, which would be being at rest, traveling at constant speed, slowing down, or speeding up. So when I look at the first one, what is the direction of the acceleration? Well, it's to the left. And the car is moving to the left, so its type of motion would be that it speeds up. In B, the acceleration is to the right, but the car is moving to the left, so it's going to slow. And in C, the acceleration is 0 because the dots are constantly spaced. So it's traveling at a constant speed. All right, so let's practice one more time. In A, will it speed up or slow down? In B, will it speed up or slow down? In C, will it speed up or slow down? If you guessed it right, if you said it speeds up, it slows down. It slows down and it speeds